Hello everyone, my name is Sam Dow, and I am an application engineer from Microsoft. So in my presentation today, I'm going to be talking about advanced symbolic and numerical techniques for vibration analysis and attenuation in Maple and MapleSim. So we all know that all rotating machinery systems experience oscillation to some degrees during startup, shutdown, and continuous operation. So consequently, the torsional response characteristics of rotating and reciprocating equipment should be analyzed and evaluated to ensure the system's reliability, because excessive vibrations can result in gear wear, gear tooth failures, or broken shafts. So this is very important to prevent machine breakdown or reduce noise level, or improve operators' comfort level. Improving machine performance and reducing energy consumption is also a very important goal of vibration analysis as well.
There are several different sources of vibration in a machinery mechanism, and this can come from external sources like reciprocating paths. For example, in the vibration can come from piston and slided crank mechanism in an internal combustion engine. This is because the slided crank mechanism doesn't have a constant motion. This is due to the combustion reactions in the engine cylinders causes the gas inside it to compress and expand repeatedly, and producing the periodic fluctuating gas torque that applies on the piston surface. This causes the piston and slided crank to have a periodic fluctuating motion as well. In most systems, this is the most dominant source of vibrations. The total engine torque is the combination of the individual torques of the individual fluctuating torques that are coming from different cylinders. For example, for a four-cylinder internal combustion engine, the total torque is the sum of the individual fluctuating torques that come from four different cylinders. So this can be very complicated, and for if we have a higher number of cylinders, for example, for a 12 cylinders or for a double engine driveline systems, this can be very complicated and challenging to understand and analyze. The other components can contribute to the vibration of machinery structure as well. For example, the vibration can also come from pumps, generator, air conditioning compressors, or other non-reciprocating parts. For example, unbalanced shafts and wheels, hook joints, propeller, backlash in gearbox. And the other important source of vibration come from internal, this inherent property of the shaft or the driveline. For example, the vibration can be caused by the self-excited instability due to the natural vibration frequency of machine structures. And it is crucial for an engineer when they design drivelines that they have to avoid this natural frequency completely, so that to make sure the frequency of the external vibration does not coincide with any of this natural frequency. In general, there have been two approaches to vibration analysis of mechanical structures. The first one is the finite element approach. This is a numerical technique where a system is discretized and idealized as thousands of basic elements. For example, this element can be beam, triangular, rectangular elements, and this results in solving a huge system of thousands of linear equations, and therefore it remains very time-consuming and very expensive. So recently, it has become increasingly common to use lump mass model combined with experimental measurements. This approach can be expanded to develop more sophisticated models to assist understanding in ensuring high levels of refinements. So now let's get to a practical problem in order to understand how vibration analysis can be done in MapleSim. For example, a customer may come to you and they say, well, I have a driveline, which I have all the properties such as the engine data, the stiffnesses and damping coefficients of all the shaft components. I know the range of speed that the system is spinning, and I want to do an investigation to understand why the system makes so much noise, or to know what are the weakest parts of the system so that I can improve the design to prevent a system breakdown. So this requires a complete vibration analysis for the driveline. For example, you can investigate the maximum shear stress between some certain driveline components. For example, between the cylinders 1 and 4 of the internal combustion engine, or the power loss in the flywheel in order to understand the vibration for the entire system. So for the system that is shown here, it has an internal combustion engine, a V4 internal combustion engine with a nominal power of 537 kilowatt and a nominal speed of 1800 RPM. And the driveline also has a propeller which produces a thrust to push the ship forward. So these are the two most important sources of vibrations. I'm going to get into details about this component very soon. And the shaft is represented by the masses components that is connected in series, and this and the shaft sections they have different properties. For example, they have different masses, inertials, and different spring stiffness and damping coefficients as well. The propeller and the internal combustion engine are connected through a transmission which is modeled as a simple reduction gear, and there's also a flywheel that is attached to the crankshaft, the first crankshaft of the internal combustion engine to reduce the vibration on the internal combustion engine, and there's also a pump that is attached to the end of the driveline as well. Before we get into the details of the model, let me give you a little bit overview of the MapleSim software. So this is the MapleSim GUI. In the middle of the in the middle of the screen, you see it is a workspace where you construct the model diagram. So in order to build a model in MapleSim, you simply drag and drop the component from the component library on the left-hand side onto the workspace and connect them together. And for 3D mechanical models, you can actually view the 3D animation after every simulation. So you can see the plots and animations, and you can also easily change the model and component parameters on the panel on the right-hand side as well. So there are several different ways you can develop a vibration model in MapleSim. You can either develop the vibration problem using one-dimensional mechanical component or 3D mechanical component, and this would produce the same results. But the 3D or the multi-body MapleSim models allows you to handle both translational and torsional vibration at the same time, while the 1D model only allows you to do vibration analysis either for translational vibrations or torsional vibration one at a time. And MapleSim also allows you to incorporate test data in also so that you can develop the nonlinear spring and damper model in MapleSim. For example, this slide shows how a nonlinear spring and damper can be modeled in MapleSim by inputting the relationship between the damping force and the damping coefficient into an Excel spreadsheet, and then attach that into MapleSim using a lookup table. So this allows you to incorporate any kind of experiment data or testing data into a MapleSim model, so that you can develop any kind of so that you can simulate any kind of nonlinearity in springs and dampers. So now let's get back to our actual problem. Structurally, this model is very simple, so it doesn't have any translational vibration. So I just use 1D lump mass system to build this model. So you can see that the most important parts for the vibration analysis for this model are the internal combustion engine component and the propeller component. And these are the two important sources of vibration for the system, and they need to be modeled very precisely. And the internal combustion engine and the propeller are the two components that I'm highlighting now. And these components are actually subsystems, so they contain more details inside this. And the shaft components, the shaft sections are modeled as linear springs and dampers and inertial components. And you can also see that I have an ideal gear, an ideal reduction gear to model the transmission part for the driveline. And I also have a flywheel that is attached to the cylinder 1 of the internal combustion engine and the pump end. So for this model, I am also attaching a sensor to measure the twisting angle between cylinder 1 and cylinder 4 of the internal combustion engine. So this would allow me to calculate the deflection between the shaft section between cylinder 1 and cylinder 4, and then calculating the shear stress, the maximum shear stress for this driveline section as well. And I also attach a probe to measure the power loss for the flywheel that is caused by the flywheel attached to cylinder 1. And this is a little bit more detail of the propeller component, which is modeled as a combination of two sinusoidal functions that have different frequencies and phase angles. The most predominant part for the source of vibration are coming from the internal combustion engine. And this is due to the gas pressure torque that is related to the cylinder gas pressure by the geometry of the slided crank mechanism that causes the vibrations. So this gas pressure torque repeats after every complete working cycle. For example, for a 4-stroke and single-acting engine, the interval of the repetition of the of 2 revolutions of the crankshaft or 2 pi's. For 2-stroke engines, it is 2 pi's, and therefore the gas pressure can be represented by a Fourier series as given by this function. So this function has 2 parts. So the first part is a steady part, which is a function of engine geometrical parameters, and this part doesn't. This steady part doesn't excite vibration, and in general can be omitted from the vibration analysis. And the 2 important parts are the sum of the sine and cosine components that you see at the end of the equation here. This is the fluctuating part, and it is represented by sum of sine and cosine components. And it is the parts that we have to model precisely. And more specifically, we need to determine the amplitudes Ck and Sk of the sine and cosine components. So these amplitudes Ck and Sk can be determined either from simulation or experiment data. In the industry, this can be done using by measuring the cylinder gas pressures for different engine speeds and load conditions on an engine testbed using a pressure transducer embedded inside the combustion chamber. H0 is the maximum of harmonic terms or harmonic orders. It is the number of excitations received by the system during 1 revolution of the crankshaft. The value of H0 can be infinite, but in practice, in general, 12 harmonic orders are usually used because they provide good enough information for modeling the gas torque in the combustion chamber. and for all the higher order, they don't contribute too much to the overall vibration to the overall engine torque, so they are usually neglected. For a four-stroke engine, the harmonic orders are usually half multiples. For example, we have half order, one order, and then 3/2 orders as well. So, so normally for a four-stroke engine, we use 24 harmonic orders. So for the engine, the figures that so the image that you see on this slide, you can see that we have a sine and cosine amplitude, CK and SK terms for 24 orders, and each order is represented. In fact, we have 24 columns data for a four-stroke engine because we have half orders as well. For a two-stroke engine, there are no half orders, and all the orders are integer multiples. So we only have 12 columns for the engine, the gas torque data. In the case of multiple cylinder engine, there's a phase difference between the fluctuating torque for each cylinder. So this phase is related to the firing order of the cylinder, and this is taken into account into the MapleSim model as well. So for a MapleSim, so for the vibration analysis models that have been MapleSim, you can simulate misfiring cylinder with open valves, or you can simulate the loss in the engine power due to the misfiring as well. The vibration analysis in MapleSim can be done through just by using MapleSim alone, or using the vibration analysis template. So the vibration analysis template in MapleSim is a template that was developed for this kind of study. So it has two parts. So the first part allows you to define some motor parameters, engine parameters, for example, the number of cylinders, engine nominal power, engine nominal speed, the area, the area of the surface area of the piston or the crank radius. You can also load up the excitation table for the internal combustion engine as well by simply clicking on this button. So this allows you to incorporate experiment data into a MapleSim model. And after this, you can actually plot the mean effective pressure for the engine. So the mean effective pressure is a measure of the engine's capability of so it is a measure of the engine's capability to do work. It can be thought of as the average pressure over a cycle in the combustion chamber of the engine. So this quantity is dependent on the engine speed in RPM, and it is used to find the amplitudes for the 12 harmonic orders. So it is a very important quantity that we have to calculate the MapleSim. So after you load up the engine excitation table and define the parameter for the simulation, you can run the simulation either from MapleSim model or by clicking on simulating MapleSim model in the Maple worksheet or the vibration analysis template. So for example, here you can define the simulation time step. You can also sweep the vibration over a range of engine orders. So for example, here I enter 1 for the minimum for the mean engine order and 24 for the maximum engine order. So we can simulate and extract the maximum stress for the 24 vibration orders. You can also select the plots that you want to display on the plot window on the left-hand side, and you can also click on the Run Order Analysis button at the bottom to do the engine order analysis or engine order tracking. It is another question that many people would like to ask is how to simulate engine misfires in MapleSim. It is quite possible to simulate engine misfiring or a cylinder with open valves by simply turning off one or more cylinders, or just by simply scaling down the engine output torque during the simulation. So as an example, this figure shows the torque loss for a 4-cylinder engine. This graph also indicates a 70% power loss in cylinder 3 due to misfiring. So it is represented by the yellow curve on this plot. One of the unique features of MapleSim is that it is built completely on a fully developed symbolic Maple engine. So it inherits all the symbolic capability of Maple. So this allows you to extract the symbolic equation for any models that are built in MapleSim. For example, you can build a crazily complicated model in MapleSim, and with a few clicks, you're able to generate the governing dynamic equation for the entire model, or for whatever components that you select. So this is important for vibration analysis, as you can compute the stiffness matrix for the systems. This screenshot shows how I use a few Maple commands to extract the differential equations, the dynamic equation for the entire driveline, and then obtain the stiffness matrix. And this would allow you to calculate the eigenvalues, eigenvectors, or the natural frequencies, or the mode shape for the model. And this is shown on the next slide. So the figure in the bottom of this slide shows the mode shapes of the vibration, the vibration mode shapes for the driveline for the 7 natural frequencies. So there are a lot of information you can read from this plot. For example, you can know, for example, you can have an image of the shapes of the vibration for a certain natural frequencies. You can also investigate like which sections is the shortest section for the driveline as well by just looking at this plot. Vibration resonance occurs when the frequency of a peak in the excitation coincides with one of the natural frequency of the systems. Because the excitation frequency changes with engine speed, it is clear that a wide range of excitation condition will occur throughout the engine speed range. It is therefore crucial to plot the vibrations for in the individual harmonic orders over a range of engine RPM in order to investigate which component or which part of the driveline have the most contribution to the overall vibration of the system. For example, this 2 plot shows the maximum shear stress, the top one, and the vibratory torque on the propeller, the bottom graph, over a range of engine RPM for each individual harmonic order. So we have 24 order here because we have because we have a 4-stroke engine. So by looking at this graph, you know which vibration order or which harmonic orders contributed the most to the overall vibrations. And you can also plot the vibrations, the individual shear stress or vibratory torque for individual order in a waterfall diagram as well, as I'm showing it on this slide. For example, here the first plot shows the maximum shear stress in z-axis for the 24 harmonic orders. So by looking at this first plot, you can see that order 1 and order 2 and order 3 contributed the most to the overall vibrations, and the contribution of the high orders like after order 4 or 5 are nearly negligible to the overall vibrations. And the second plot on the right hand side, this shows a color map representation of the first plot on the left hand side. So what is MapleSim? So MapleSim is a truly unique physical modeling tool. It is a built, so MapleSim is built on a foundation of symbolic engine, symbolic computation technologies. It allows you to handle all the complex mathematics involved in the development of engineering models. So you can build a very complicated model in MapleSim, and MapleSim would apply index reduction techniques to reduce the number equation of the model, so that allows the models to be solved faster, or it allows you to develop models that are capable for hardware loop applications or for real-time applications. And MapleSim is also a multi-domain modeling tool. It means that MapleSim allows you to put components from different domains, for example, from electrical domain, hydraulic domain, mechanical domain on one single model and simulate all of them together. You can also design controller in MapleSim very easily. And MapleSim also leverages the power of Maple to take advantage of the extensive analytical tools. For example, once you develop models in MapleSim, you can take advantage of the a number of toolboxes that we have in Maple. For example, optimization package, control design package, to do the various analysis on the MapleSim model that you develop. And the causal modeling approach in MapleSim also allows you to reduce the model development time from months to days while producing high fidelity and high performance models. You don't have developing models in MapleSim. You don't have to worry about deriving the equation for the models. All you need to do is to connect the components together, because all the equations for each component are hard coded within each component. So that's the end of my presentation today. Thank you for your attention.